when we look at the standard addition and standard multiplication operators, we're looking at the additive inverse and the multiplicative inverse, which if we add the additive inverse, that is our subtraction. So how does that work? How do we subtract? How do we add the multiplicative inverse? And if we multiply by the multiplicative inverse, that's the division operator. So if I want to add, I use one operator. If I want to divide, I use another operator. And the last thing is, how do we get the length of the number or the size of the number or our absolute value? What about these properties? What is their, or how do we incorporate them when looking at complex numbers? So the first thing that we're going to look at is subtracting complex numbers or adding by the additive inverse. And here, what we can think of is we can think of as Z1 plus negative Z2, or the additive inverse of Z2. And we'll show shortly that negative Z1 and minus 1 times Z, or negative Z2 and minus 1 times Z2 and adding the additive inverse of Z2 are all the same thing. You can prove they're all equal. But if we look at it, when I take that negative 1 and I expand it, we get this nice form, A minus C plus B minus D all times I. And this is relatively simple. For division, it's not so simple. Somehow we have to use our multiplication the auto erasing isn't working. Multiplication, addition, and subtraction operators to create an operator that acts like division for the real numbers. And what do we mean by acts like division? Well, if A times B equals C, and A, B, and A does not equal 0, then B equals C over A. This is what we're looking for. And note, you could also have this be B does not equal 0, then A equals C over B. Because it's commutative, because complex multiplication and complex addition are commutative, this idea kind of works. And what we can do is we can take advantage of the derivative operators of real numbers. So we know what 3 divided by 5 is. We know how to divide by real numbers. So as long as I'm dividing by a real number, I'm able to somehow create the idea for division. And what I'm going to do is I'm going to turn the denominator into a real number. I'm going to rationalize the denominator. This is a technique that you may have seen in calculus before, especially when you're looking at limits. So if I have, so consider Z1 over Z2 equaling A plus BI over C plus DI. I want to somehow make this denominator a real number. And to do this, I'm going to multiply by C minus DI over C minus DI. This is going to equal A plus BI times c minus di all over c squared plus dic minus cdi minus d squared I squared. These terms here will cancel out with each other to give me a plus bi times c minus di all over c squared plus d squared. As this I squared becomes minus 1, which cancels out with this negative term here. And if we expand further, what we can see is that we get a squared ac plus bd I, or plus bd over c squared plus d squared plus cb minus ad I over c squared plus d squared. And this is the output, which is a complex number. But we're dividing, note, we are dividing by a real number, which we're allowed to do. We know how to divide a real number by another real number. So we now have a way of dividing complex numbers. Now, what is this term? And what is this term? Well, that is, it actually has a term. It's called the complex conjugate. And let's explore this a little bit. What is the complex conjugate and what other properties can it have? Well, the complex conjugate of z, denoted z star or z bar, is defined as z bar equals a minus b. So we take the same real part, we negate the complex part. And we actually can use this term to define something that's similar to our length of a vector. So if I look at this, and I was thinking of this as a normal length of a vector, the 1, 2 vector, which we had before, 1 plus 2i. I wanted to know the modulus of this was. I'm going to figure out what the length of this vector is. And here, this is 2, this is 1, and it's a right angle triangle. So the way in which I would calculate this vector, I would take the square root of these terms. The modulus of z equals square root of these terms, which if I look at it, this here, remember, this is the real part of z, and this here is the imaginary part of z. So it's equal to the real part of z squared plus the imaginary part of z squared. Now, that's how we define what the modulus of z is. And if we look up to what we did previously, we can kind of get a hint. Well, here, if we look at our number on the denominator, c is the real part and d is the imaginary part. And it's the real part squared and the imaginary part squared. So what did I multiply here? Well, I multiplied the number by its complex conjugate. Turns out that the modulus of z squared is equal to z times the complex conjugate of z. which means that we can simplify our definition of division really nicely. We get that Z1 divided by Z2 is Z1 times the complex conjugate of Z2, all divided by the modulus of Z2 squared. Now, I highly encourage you to practice, so I'm going to give you a few examples. Compute the following. 3 plus 2i plus 4 minus 3i, all divided by 2 minus I. The modulus of 3 plus 4i times 2 minus 3i. And show that the modulus of Z1 times the modulus of Z2 is equal to the modulus of Z1 times Z2. Finally, show that the modulus of Z or 1 divided by the modulus of Z is equal to the modulus of the multiplicative inverse of Z. Hope you guys have a wonderful day.